Hey, what's up, Logic fans? It's Ash, and today we're going to hit section 3.5, our fifth section on propositional syntax, axioms, and central syntactic concepts. This is one of my favorite topics in logic, axioms. Let's rock. Okay, let's jump straight in here, and I want you to consider this sentence. If A, then A. Now, I want you to cheat for a second, even though we're doing syntax. I want you to stop for a minute and think about this sentence semantically for a second, okay? So semantically considered, is this sentence a logical truth, a tautology? Is it a logical falsehood or a contradiction? Or is it a logical contingent? Okay, hopefully you recognize by now that this is in fact a logical truth, all right? Go ahead and run your truth table to prove that. Now, here's the thing. Up to now, what we've been doing is we've been going over these different rules of syntax, right? So you got De Morgan's and modus ponens and modus tollens and all these things, right? There's a ton of them. And you're given some strings, you're given some premises, and from those premises, you're asked to sort of manipulate them using the rules to arrive at a new sentence. And once you've been able to carry that out, we say that, you know, the initial strings, the premises, logically imply or you can validly infer from the premises the concluding string that you come to by application of the rules. Okay. In this particular situation, I want you to imagine a situation where we're trying to prove this thing to be true. Okay, and pardon me, you're not trying to prove it to be true. That's a semantic concept. You're attempting to deduce syntactically using your syntactic rules this particular sentence. Now, ideally, this particular sentence should be deducible even if you have no premises to start with. And the reason we want it to be deducible even if you have no premises to start with is that semantically viewed, this is a logical truth. And so we would prefer a logical system which allowed us to absolutely deduce this even if we had no premises available, right? This should count as a truth of logic. And so we would want a syntactical system that allowed us to syntactically deduce this string, okay, this uninterpreted meaningless string, even if we didn't have any premises. You can think of axioms as things that allow us to do that, okay? Axioms allow us to deduce strings without the benefit or aid of any premises whatsoever, okay? So let's take a look at our first axiom. Our syntactic system has two axioms. The first one is LEM, okay, the law of excluded middle. And what it states, very roughly, is that from no premises whatsoever, you can write down any sentence or any string of symbols of this form, and you're going to justify it just by writing LEM, and then you might have to identify your proposition P. Okay, so let's look at an example of this in action. So let's play permissible or impermissible, permissible or forbidden. Okay, each of these four situations is arguably, or the person is alleging that they've used our first axiom, law of excluded middle, LEM, legitimately. And the question is it legitimate? Okay, so for example, this person just decided to write down on their paper A or not A by LEM, and you have to determine whether or not that's a permissible or an impermissible use of our axiom. And if it is permissible, what was the value of P that the person used? Okay, so let's go ahead and give you a second to pause and try this, then we'll come back and do them together. Okay, so hopefully you've got a chance to pause and think on this. So this is the first one here, A. This is absolutely permissible. You can use LEM this way. You can just sort of, at any point in any syntactic deduction that you're using, whether it's got premises or not, but we're thinking about the cases that do not have premises, you can write down, anything of the form P or not P, and then write LEM, okay? And so in this particular case, the value of P was just A, right? And so hopefully you can see that here, all right? Now, was this use of LEM permissible? And the answer is no, it wasn't permissible at all. What would the value of P be? Okay, now of course you can get this. First you would get this by LEM, and then you would apply com to this to get this construction. So it's obtainable, but the question before us is whether it was obtainable by use of LEM and LEM alone, and the answer to that question is no. Use of LEM does not permit that you to get this directly. Okay. All right. Now, C, is this permissible or impermissible? Can one obtain this using LEM? And the answer is yes. And this is a really good type of case to keep in mind. You can absolutely use this. Okay. In this particular case, P is just not A, right? So if this whole thing here is P, then notice P appears again right here, and then you've got not P. So this is P or not P. It's just of this form. Okay. So this is absolutely allowed. What about this last case? Is this a legitimate use of LEM? Is this permissible? Yes, it is. This is absolutely permissible. You can do this type of thing. Anything of this form, okay? So in this particular case, P is just this whole thing, right? And so you're allowed to go ahead and do that. These are all permissible uses of our first axiom, law of excluded middle. And okay, what I want to do now is I want to try to show you how we might actually use LEM in an actual deduction. In particular, let's show you how you can use it to derive if A, then A, that sentence we first started thinking about. So let me give you that example. So I'm going to introduce a new symbol here. This symbol right here, this is the turnstile symbol. I'm going to be explaining some central semantic concepts in a little bit later in this video, okay, where this will play a prominent role. For now, you can read this thing. This is called the turnstile symbol. Let me write that so that you can see it 100%. Okay, so that symbol is known as the turnstile symbol. Okay, and the turnstile symbol is to be read something like it is provable that. So in this particular case, it says it is provable that A implies A. This string is provable. That's what it means, okay? Other times your professor might talk about it as saying it is a theorem of logic that, or it is a theorem of, if we're taking our particular class, bivalent logic that A implies A in this particular case, all right? So it is a theorem of bivalent logic that this thing, whatever follows here, okay? In this case, A implies A, or this particular string, if we're thinking about it purely syntactically as we are, okay? Also, you can interpret the turnstile as sort of giving you directions, and that's what I'm doing here. I'm giving, I'm saying prove that such and such is a theorem of logic. Okay, so where the x is here is, in this case, it's this guy. Okay, so I'm saying prove that this string of symbols is a theorem of logic. So you can interpret it as me giving you some directions for what to do. And let me show you how you're going to do this. I'm going to give you some hints along the way. Okay, and once again, I want to reiterate, this should be provable. This should be deducible in our syntactic system, even without premises, because it is a tautology, right, viewed semantically, and ideally we would want a syntactic system that allowed us to deduce these kinds of things, okay? So I'm going to show you how we do that in our system, and we're going to use the law of excluded middle to do it. Okay, so I'm going to give you a little bit of a hint here. So we're supposed to, from no premises, generate this string, okay? Now, what I'm going to do then is, since I have no premises, I'm going to start with one of my two axioms, which is basically my only option, because without premises, I don't have any strings to start with. And my axioms are what I can invoke even when there's nothing to invoke them on. They're sort of like freestanding principles that at any point in any argument, any line of deduction, you can just sort of say, well, P or not P. Okay, we're also going to have one more. But in this particular case, I'm going to start off by saying A or not A, and now I've got something on the board. And the idea is now that I've invoked my axiom to get something on the board, and I could write, P equals A in this case. Now that I've got something on the board, I can apply all of my other syntactic rules that we've been going over in 3.1 through 3.4 in order to derive this. Okay? So let me give you a little bit more of a hint here. So there's basically a couple of steps you can do here in order to get this. So I'm going to leave this blank, and I'm going to leave these two blank as well. So your job is to see if you can fill this in and these two in order to prove that this string of symbols is in fact a theorem of logic. I'll explain what that is shortly. From no premises whatsoever. So pause now and see if you can fill in 2 and the justifications here. All right, hopefully you've had a chance to pause, okay, but I'm going to reveal it now. So what you're going to do here is you're going to use this rule to get this, which was com on 1, and then of course we used impl on 2, okay, in order to get this sentence into this form, which is this. And this here is what we call a proof, okay, that this whole thing here, let me show you, this whole guy here, okay, this is a proof that this string of symbols is a theorem of logic because we have this syntactic deduction here that does not involve any premises. Okay, so I'm going to define all those concepts shortly in a second. You might have questions about how did you know how to do this to derive that. I'm going to talk more about that later. But that's the basic concept for now, that this whole thing here proves that this string of symbols is a theorem because you've got a syntactic deduction of this from no premises. That's the big concept. And in fact, since I've just been helping myself to these concepts, I think it's time to just lay out the concepts that I'm using and formally define them and what I mean by them, okay? So let's do a little bit of an overview of some of the concepts that are in play here in addition to the notion of an axiom, all right? So we've got the notion of a syntactic deduction. I'll explain that shortly. We've got the notion of a syntactic proof, which is actually different than a syntactic deduction, as I'll explain, and I've already hinted. We've got the notion of a theorem, okay, which is closely related to the idea of a proof, okay? And then we've got the notion of syntactic validity or being syntactically valid. So let's jump into each of these right now, starting with perhaps the broadest notion and then sort of working our way down here, the notion of a syntactic deduction. Okay, so, this looks super intimidating, this definition of a syntactic deduction. Don't let it intimidate you because you've already been working with syntactic deductions the whole time. I've just never taken the moment to formally specify them. You've been doing syntactic deductions in 3.1, 3.2, 3.3, and 3.4. This is just a formal regimentation of what you've already intuitively been doing. So, a syntactic deduction is I'm going to read this through and then I'm going to give you an example. It's an m×2 grid, I'll explain that, where every quadrant in the leftmost column contains exactly one string, and every quadrant in the rightmost column indicates whether the string to its left is a premise, an axiom, or follows from one or more previous strings by a syntactic rule. Whew. Okay, what a mouthful. What is going on here? What does that mean? Okay, this right here, okay, this is an example of a syntactic deduction. You've been producing them all along. Notice, this is an m×2 grid. In this case, m is 3. 1, 2, 3 rows and 2 columns. 1, 2 columns. So it's this right here, okay? All right, it's those. And every quadrant in the leftmost column contains exactly one string. So here's a leftmost column. It contains a string. Here's a leftmost column. It contains a string. Here's a leftmost column. It contains a string. Fine. Exactly one. It doesn't have 2. It doesn't have 3. It doesn't have none. Okay, so sometimes I put the blank space in there. You can just sort of picture those as absent. I just do that to make things easier to read, but we can picture it without it. And every quadrant in the rightmost column specifies whether the string to its left, so, this quadrant here is going to specify whether the string to its left, which is this guy, is a premise, an axiom, or follows for one or more previous strings by a syntactic rule. Like this one is a syntactic rule. We didn't have LEM in this one, but you could, okay? And that's just what a syntactic deduction is, all right? For us, it's just a grid like this, okay, that you've been doing all along that satisfies this whole big description and behaves in exactly this way. Okay, running a little low on time. Let's spill this into the next video, 3.5b, while we continue the discussion of these central semantic concepts. See you on 3.5b.